I will talk about my recent work that appeared at the recent crypto conference. So in this work, me with my advisor and a collaborator, we built a non-interactive zero-knowledge argument scheme based on two assumptions called LPN and MQ. So I'll explain what all these terms mean in a bit. And yeah. So this work is roughly about proof systems. And in particular, we care about a particular form of proof system called non-interactive zero-knowledge proofs. So in a proof system such as NIZK, it consists of two parties, a prover and a verifier. The prover will try to convince the verifier that some statement is true based on its private witness value. And this has been a fundamental notion in cryptography. It was defined all the way back in the 80s, and it has actually found a lot of applications in practice. But first, let me just talk about what the proof system should guarantee. And in this case, the proof system should guarantee three properties. The first property is that it should be complete, meaning that an honest prover would convince an honest verifier. And it also should be sound, meaning that the verifier should reject any statement that is not in the associated language to be verified. And this is regardless of what the malicious prover may do. It may send any proof string, and the verifier should reject with overwhelming probability. And finally, we also have this very nice property called zero knowledge. And what it is that the proof pi here can be simulated by some algorithm called the simulator. And this algorithm only knows the public statement X. It doesn't know the private witness W at all. It has some sort of extra power over the verifier in the sense that it may also generate this common reference string by itself. So it may embed some trapdoor in it. But intuitively, what zero knowledge means is that the proof can be generated in a way that does not even requiring the witness, and hence the proof doesn't leak anything about the witness. Okay, so lots of practical applications right now. There are lots of proof systems that are being deployed and actually securing a lot of money in various blockchains. So very important and also very exciting primitive.
I have a question.
Yeah.
So for all the applications other than the ZK rollup, which basically use this extensive property.
Yeah.
Are there any other applications that also use that, or all the other properties only focus on this property?
So, yeah, sorry. There we go. So zero knowledge is quite important in privacy applications. Voting, I think, is one of them. You also want, like, if you want to prove image transformations, you don't want to leak the original image. If you want a private blockchains, you don't want to leak the transactions. And so all of those things need zero knowledge.
Okay, so I'm just curious about any other applications that only use the thickness property other than ZK rollup. I don't know any.
I see. I feel like the succinctness, besides ZK rollups, you just want to prove the correctness of some large computation. Like if you want to show any kind of large computation, like an example might be you have a mathematical proof of some theorem, and then you would want to verify that the proof checker ran the checking computation correctly. And in that sense, like if you have a proof of the Riemann hypothesis, right? You don't necessarily need to hide the proof. You actually want, like, it's fine if you just publish the proof.
Yeah, you can also think of like this outsourcing computation, right? Like you have some small entity which does not have a lot of compute power, and like it outsources some computation to a larger entity, like say Amazon, AWS, or something. Like along with the computation, like they can send the proof back showing that it did.
So yeah, this work is not about constructing NIZK that are efficient. This is about constructing NIZK that are provably sound in the plane model. And let me tell you what that means. So in practice, in order to get concrete efficiency, we usually rely on some idealized models, such as the random oracle or idealized groups. But in theory, we want to achieve NIZK from the most basic assumptions possible. And that means that we don't want to rely on any of these idealized models. And actually, when you reduce the task to just having NIZK in the plane model, it's quite difficult to construct. For a long time, the only constructions we know were from either factoring or from bilinear maps. And this only changed in the past, say, 7 years, with recent progress on this primitive called correlation-intractable hash functions. And this allowed construction from a lot of new assumptions, such as LWE, which is a lattice-based assumptions, but also combinations of assumptions such as DDH plus LPN or sub-exponential DDH. Okay, so these are all just acronyms for the assumptions. I'll explain the ones that we actually care about later. Okay. And in particular, if we care about post-quantum security, meaning that we want the NIZK to be secure even against quantum attackers, then the only construction we know is from the LWE assumptions. And this is the motivation for this work, which is that we want to search for new constructions of NIZK that are post-quantum secure.
Does the start also they argue that they are post-quantum?
Yes, and they use random oracles. Yeah. Okay, so let me try to further motivate why we should care about this task. The first is that we should always be trying to diversify the constructions for a given primitive. Because what happens is, what if one primitive gets broken, one assumption gets broken something? And if all we know to achieve in a primitive is construction from that assumption, then we're suddenly left with no plausible candidates left, right? And also, this is especially acute in post-quantum cryptography because lattices, from them, we essentially know basically everything, maybe except program obfuscation. But from other post-quantum primitives, we actually don't know that much. Okay. And secondly, I want to sort of understand the complexity of this NIZK primitive. Like, how simple can constructions of NIZK be? And in this case, what I mean is that the existing constructions based on learning with errors, they rely on some very heavy techniques that also give rise to fully homomorphic encryptions. But morally, NIZK should be a much weaker primitive and hence can be achieved by much weaker assumptions. Also, there was a recent work by Brent Waters. They have this somewhat simple constructions, but it's not quite ideal yet.
So this the constructions from LWE, for example, do they also like additionally require circular security or?
No.
So like it's somewhat at least not stronger than it. It's like
right, slightly weaker. Yeah. Yeah. Although if you want to get like some things CRS or something, then you do need FG. Yeah. Okay. And finally, beyond NIZK, there are these other proof primitives that actually care about succinctness, as you said, more than just zero knowledge. So these primitives are batch arguments or BARCs, or succinct non-interactive arguments, and so on. And these primitives actually turn out to be more difficult to construct than NIZK And so the hope is that if you want new construction of these primitives, we should first start with NIZK and then try to build our way up to more advanced proof systems. Okay, so the central question of this work, which we answer, is that can we try to build NIZK from other post-quantum assumptions than lattices? And ideally, the assumptions should have a long history of cryptanalysis and should be widely believed to be secure. Okay, and so in our work, we does this. We construct NIZK based on two well-studied post-quantum assumptions. LPN stands for learning parity with noise, and MQ stands for multivariate quadratic. In fact, we use a slight variant of multivariate quadratic, which has a reduction from MQ with exponential security. So so this MQ thing is we require slightly stronger security than is usually required. And I'll talk more about this later. I think trying to remove this requirement from standard MQ with exponential security is still an open problem and very interesting one. Okay, the way we construct this NIZK is that we rely on recent progress, as I mentioned, on correlation-intractable hash functions, or just CI hash. And we construct a new CI hash that is extremely simple and is CI against an expressive enough class of functions or relations that allow us to give rise to NIZK. Okay. And this CI hashing is the main contribution of the work, and it relies on this approximate MQ assumption. Yeah, I should also mention that the MQ assumptions have so far been not very well studied, as in we know that it is hard, but it is very difficult to build anything from that assumptions. And so our work, I think, is a very exciting addition to the things that MQ can do.
So basically, after building CI hashing,
Yeah.
Is the technique from CI hashing to NIZK already known, or you guys need to do it?
Yeah, it's sort of already known, and we just need to make an observation, essentially. Yeah.
So this approximation thing, is your technique like similar to this Dense-Sparse paper?
Yes, so we'll follow that template. Yeah. Okay, and finally, our NIZK only satisfy soundness and zero knowledge against computationally bounded adversary. But we can upgrade it so that the zero knowledge property is statistical, meaning that it holds even for unbounded adversary. And this requires a new variant of LPN called Dense-Sparse LPN. This appears in a companion work, sort of, also by me and my co-author. So if we have time, I'll go a bit into this assumption at the end of the talk. Okay, and the upshot for those who know about the template is that it allows us to have a lossy public key encryption scheme with approximate linear encryption and also very low correctness error. And this is like a primitive that is needed to plug into this template. Okay, so as an upshot, here is the landscape of NIZK after our work. Okay, we have all the prior constructions, and now we have these two constructions from our work. And these ones are the only post-quantum ones besides the one from learning with errors. Okay. So for the rest of the talk, I will first recap how we can build NIZK from this correlation-intractable hashing. And then I will talk about how we build our correlation-intractable hash and how we prove its security from this approximate MQ assumptions. And finally, I'll talk about just how we put things together. Okay.
So far, this prior work by this the DDH, like for example, the names from South Front to DDH, like there, the zero knowledge was statistical, right?
Yeah. And it's because you can get lossy PKE from DDH. Okay. Cool. So let's look at one particular NIZK. this will be the one that we study today. So this is a proof system for a very particular relation. It's the relation where your statement is a graph G, and your witness is a cycle, it's a Hamiltonian cycle of G, meaning that it contains all the vertices of G. And this problem we know is NP complete. So if we get a proof system for this one, then we can reduce all other NP relations to this graph Hamiltonian relation, and then we apply the NIZK proof system to that. Okay, so we just care about this, and the protocol goes as follows. So first of all, this protocol, as I state here, is an interactive protocol. It is not yet non-interactive, and we will make it non-interactive later on. Okay, so in the first round, the prover is going to sample a random permutation, and then it's going to encrypt using some public key that is in the CRS, encrypt the subgraph H, but permuted by this pi. So essentially, you're just sending an encryption of a random cycle. Okay. So in particular, it doesn't even depend on the graph G at all. Okay. It's just a random cycle. You sample it and then you send it. The verifier is going to send back the challenge either 0 or 1. And then depending on the challenge, the prover is going to do one of two things. Okay, so if C is 0, then it's going to reveal the permutation pi and the non-edges of pi applied to G. So essentially, you have G, you have H, which is a subgraph, and you want to reveal everything that is not part of H. And then when C equals 1, you reveal H itself, well, up to this random permutation. And the verifier is going to check that either if C is 0, then the revealed edges, they're indeed non-edges of pi G. It can do so because it knows G, it also knows pi because it is revealed. And so it should know what are the non-edges of pi G. So this is checkable. If C is equal to 1, it will check that this pi of H is indeed a cycle. So that is the protocol. And the claim is that this protocol, first of all, it is perfectly complete. This is sort of easy to see. If you just follow the protocol, then the verifier should accept. What's harder to see is that this has soundness error exactly 1/2. So if G does not have a Hamiltonian cycle, then the verifier will reject with probability 1/2. And this is because if G is does not have a Hamiltonian cycle, then either one of these challenges, the prover will fail to answer. If somehow it can answer both, then it actually is the case that the prover knows, it is the case that H is a Hamiltonian cycle of G, or like G has a Hamiltonian cycle because you just combine the responses from the two challenges and you match them together, and there you have the Hamiltonian cycle.
So what does it mean by non-edges? Does it mean like, okay, originally like vertex 1 and vertex 2 don't have edge between
So
them. After permutation, they still don't have edge between them. So basically it reveal like
So by committing to the graph here, I mean committing to like the adjacency matrix. Okay. So it's like ones and zeros. So you reveal all the zeros. The zeros are the non-edges.
So why don't you just reveal the edges of pi G?
I guess it's the same.
Yeah.
I guess it's
Yeah, no, like no, I was just curious why did you like present it like that?
Yeah. Let's see. Yeah, it should be fine. We don't, we don't need to have G. So yeah, should be fine. Yeah.
How is A used by verify?
Oh, so A is sort of a sign. Oh, okay. Here's why it must reveal non-edges, because the non-edges will also correspond to the non-edges of A. So what it does is it just reveals part of the encryptions. And so it cannot, and so it can reveal the non-edges of G, which are also non-edges of H, but it cannot reveal the edges because H is like just part of G, it's not all of G. So A, you could think of a bunch of encryptions, right? For every every entry in the adjacency matrix, you would encrypt that entry and you would send it to the verifier. And then in the response, you're going to open up some of them. And so that means you can only open up the non-edges. Okay, so I'll let you think a bit more about that. And also it's honest verifier zero knowledge, meaning that if the verifier behaves honestly, then this protocol is zero knowledge. And essentially it is because, first of all, you can just simulate the first message to be whatever. And then for the response, the crucial point here is that the simulator can now try to pick the challenge first, and then compute the encryption and the response after picking the challenge. So again, another exercise for you to convince yourself that it has all these properties. Okay. So now the next step is that we want to make this into a non-interactive proof system, and we do so by eliminating this interaction. This interaction is basically the verifier sends the single challenge C, and we want to remove this by just letting the prover derive C by itself. It does so by hashing the first message, and the intuition here is that if the hash is sufficiently close to a random function, then C is sufficiently random and sort of unpredictable by the, well, not unpredictable, but sufficiently random to P. And so we should get the security of the interactive version. But actually trying to prove this intuition is a little difficult.
You don't have the input.
In this case, the first message is sort of inputs independent, so we don't quite need that. Yeah. Okay. So the property of the hash function that allows us to go through with this transformation is called correlation-intractability. And the definition of it is that, say you have some relation R. We're going to say what this relation is later. Okay, so you have some relation R, and you want to be able to say that the adversary A here, given the hash key sampled at random, it cannot output some input X such that X and the hash of X satisfies this relation. So it should always be impossible to do this over the random choice of the hash key. Okay, and so the relation R that we care about for this particular example is the relation called the bad challenge relation. So this relation, the statement is the first message, and the witness is the challenge. And the relation is satisfied if from this first message and the challenge, you can somehow find a response Z such that V accepts on this this whole transpose.
The witness is Z, right?
Oh, there's no witness here. Z is the third round response. So if X, what you want is that if the instance X is somehow not in the language, meaning X here is the graph, right? If the graph somehow doesn't have Hamiltonian cycles, then you can construct some hash function that is correlation-intractable against this relation. And you can prove that if it is CI against this bad relation, then the transformation, the Fiat-Shamir transformation would go through. Okay. And then here's the reason why I chose this protocol. The reason is that this protocol has a unique batch challenge. So this relation, for every A, there is only one C. And it's even efficiently computable given the private key or the secret key for the encryption scheme. And so the way that you would do it is that you would first decrypt the encryption, the first message, and then you get some graph. And then the intuition is that the prover can either cheat by not committing to a cycle, in which case you would catch it, or it may commit to a cycle, but then it will fail to answer the first challenge, the challenge C equals 0. So yeah, and so if it does commit to a cycle, it will fail the challenge C equals 0. Otherwise, it will fail the challenge C equals 1. This is why the batch challenge function is unique. Okay.
Wait, why are you caring about the case where there is a cycle? Why do you care about the case?
Oh, because the prover may cheat by just not committing to a cycle at all, like committing to some other graph.
Okay.
Yeah.
So in that case, you still have like batch challenge, but it's not. You're just in that case, the batch challenge is like
The batch challenge
it's
is
just like even the graph indeed has like a Hamiltonian cycle, but
Yeah.
probably like the prover doesn't know about it. So
yeah, it's gonna fail because if C equals 1 here, it's just gonna reveal everything, and then it's going to see the verifier is going to see that the prover did not commit to a cycle, and then it's gonna reject.
Mhm.
Yeah. Okay. So that's what we should try to build, is that somehow we should build some hash function that is correlation-intractable against this bad relation function relation. But the problem is it's kind of hard to build CI hash functions. And so first of all, we should try to simplify this bad challenge function first, before trying to build some hash that is CI against some lower complexity class. Okay. So how can we simplify this? Here we follow a previous framework by Brakerski-Koppula-Mour, and they showed that it suffices to actually just have correlation intractability against functions f that are approximable by constant degree polynomials. What that means is that your functions f have some probabilistic representations by some constant degree polynomial g that may range from some distributions of constant degree polynomials. And it should be the case that if you sample a random g from this distribution, then it should agree with f on many, say 99% of its length. Okay. And the f here we want is this bad challenge function. And well, not quite this one, but we will modify this eventually so that it becomes a function of that form, approximate constant degree polynomial format. Okay.
That means you're basically want to have like approximation of
Of
so you're inputting A,
Yeah.
you want to have like a polynomial that basically replicating the behavior of batch cow, right?
Yeah.
Okay. So I guess you probably need like A to be in some combinatorics or
Yeah.
E function is hold for any x.
It should hold for any x. Well, what is x here? Oh, that one x?
Yeah.
For a given x. For a given x, this probabilistic statement holds.
Then can that the big G depend on x?
I think so. Well, No, sorry. No, it should not. So the way you choose is, first of all, you choose the calligraphic G, which is the distribution. And then your guarantee is that for every x, then f of x should be equal to g of x with type for most of its entries when he is sampled randomly from this calligraphic G. Yep.
So like this probability is also what a random sample vector.
It will randomly sample G,
And then you want it to be over most of it, over like 99% of it. So it should also be like x is also sampled.
no, you want this to hold pointwise for every x.
Yeah.
Yeah.
No, but like if you say like if you fix x before choosing g.
Oh, no. You choose G first, and then you say for every x, this happens. Yeah. Okay. Awesome. So this function fast challenge, it does two things, right? First, it does decryption, and then it does a cycle check. And we want to squash the complexity of each of those subroutines. And so we can do this. First of all, we can find some encryption scheme where the decryption process is an approximately linear function. And luckily, we have such an encryption scheme from this learning parity with noise assumption. So I won't go too much into this, maybe at the very end. The second is that now for the second subroutine, we can try to squash the complexity by turning it into a free CNF formula. Okay, so this is your classic reduction to free sat. You can turn any computation, right, into verifying a free CNF formula with an additional witness here. The witness is the satisfying assignment. Okay, so you also need to include the satisfying assignment in some way, and we just need to encrypt and send W in the first round. And so the protocol now looks a little bit different. You're gonna also send this encryption of W in the first round, and then it's going to run this free CNF formula check. Yes.
Encryption is statistical.
No. So yeah, I'm not quite sure. But yeah.
It seems like a commitment, or more like a commitment, because you need to, but it's really fine.
Oh. Yeah. So an encryption scheme is you can see it as a statistically binding commitment scheme with a way to extract the underlying commitments, right? It is computationally hiding. Cool. So this is our new goal, which we will actually achieve, which is that we only care about the CI against CI against functions are approximable by constant degree polynomials. And let me just call this short by approximate CI. Okay, so we want hash functions that are approximate CI against this class.
So
yeah.
When you say like approximable to a free CNF formula, what does it really mean? Like,
oh,
do you have like approximation error or?
Yep. So how do you approximate a free CNF formula? Any guesses?
You'll probably take like, like each CNF is like x times like 1 minus.
But could you right on the
Sorry?
like yeah, what medium was saying?
It's interpolation.
Like if you have x, then have a term like x1, and then if you have negation of something and then have 1
minus.
Yeah. So free CNF means that every term has free variables, and then it's a conjunction, right? So let's say x1 and x2 and x3, you can linearize this. So instead you just check if x1 plus x2 plus x3 is equal to 0, or sorry, should be equal to 1, let's say. And then this is not a perfect translation, but it should hold with some like 1/2 probability. And then you can instead have a bunch of these linear equations. And yeah, the more linear equations you add, random linear equations you add, the more you can correctly approximate this formula P. Yeah. Cool. So this brings us to our second part of the talk, which is how we build the CI hash. But before that, let me mention this assumption that I have been hiding from you all along. And this assumption is actually extremely simple. It just says that if you have a system of quadratic equations over some finite field, then solving this system of equations when the coefficients are chosen at random is a difficult problem. Okay, this is all it is.
Are you guaranteeing that the system will have a solution, or like in average case, it's gonna be like not so?
Yep, great question. So it depends on the relationship between the number of variables and the number of equations. So of course, if the number of equations is less than the number of variables, then we're in this underdetermined regime where lots of solutions may exist. And vice versa, in the overdetermined regime, we don't expect any solutions to exist. Okay, and the claim is that it should be hard to solve for each of those. So for the overdetermined case, you're sort of like planting a solution, and then the adversary should find a solution. Yeah, but also the caveat here is that it's not secure for every choice of parameter. It's only secure when m is within this range between square root of n and n squared.
So when you say solving, it means like the adversary has to find a solution when there's like a solution. When there's no solution, it has to have like no solution.
Yeah, we can always slightly change the definition so that there's always a solution, and the adversary must find a solution or find some other solution. Yeah. Okay. And in this work, we care about this underdetermined setting, and with the number of equations to be slightly polynomially less than the number of variables for any epsilon greater than 0. And the best cryptanalysis prior to this work suggests that this setting of MQ satisfies exponential security. And by exponential security, I mean that the notion that a polynomial time attackers should have exponentially small success probability. Okay, so this is the notion that we're working with. Good. So let me say how we can hash from MQ. And the idea is that the hash key is your MQ instance. It contains all the coefficients for your system of equations. And then you evaluate the hash by just evaluating the quadratic functions on your inputs. And that's it. This is why we want to work in this underdetermined regime so that the hash function is actually compressing the inputs. Cool. Another fun exercise is that this hash function is not even collision resistant. You can actually very easily find a collision. The way you do that is you can choose some random offset delta, and then you solve for this equation here. This will give you a collision. And this turns out you would cancel out the quadratic terms in x, and so you're left with a linear equation in x, and you can solve for x. Okay. But it is correlation-intractable against quadratic functions. And the proof is also very simple. So let's say you have some quadratic functions, you're trying to prove that it is correlation-intractable against. And recall the definition of CI, meaning that the adversary cannot output any x such that the hash of x is equal to f of x. This is just definition once you unroll it. Okay. So now you can, because these coefficients are chosen totally at random, you can imagine in your mind a hybrid where you, instead of choosing Q and then returning as is, you would first sample random Q, and then you add in the F, and then you return it as the coefficients. Okay, these two are completely identically distributed, right? Because in either case, Q is sampled randomly. So, but however, now you see that if H with this new hash key is equal to F of X, then we're actually solving the MQ system of equations. Okay, so this means that it should be CI against quadratic polynomials. And also this even satisfies a stronger property, which is approximate CI. So even for functions that are only approximated by quadratic polynomials, we can still show security. And the proof is basically exactly the same, except that here now we have, instead of Qx is equal to 0 for all of the equations, it's going to be equal to 0 for, say, 99% of the equations. And the conjecture here, this new assumption called approximate MQ, says that this should still be hard to achieve. Even if you can choose which 99% of the equations you want to satisfy, it should still be hard to satisfy them. And this actually just follows from the standard MQ assumptions by a reduction where you guess which of the equations would be satisfied and which are not. And if you guess correctly, then you're actually just solving MQ. Okay, so how do we achieve approximate CI against more general degree D polynomials for D that is possibly any constant? Because recall, in the template for NIZK, we needed it for not just quadratic, but potentially for a much higher constant, say D equals 100, for instance. So how do we get to D equals 100? There's basically two solutions that we said in the work. The first is that we just assume the corresponding higher degree analog of MQ, which is even more plausible, because if you find it hard to solve degree 2 equations, it's probably hard to solve degree 100 equations, right? And so it just follows if you set D to be large enough so that it can fit in the template. But the downside is that it sort of blows up all of your parameters. And also people haven't sort of studied this as much. It's clearly harder, but we would like to achieve it from the sort of the weakest assumption possible. Okay, so let's just try to achieve it from just MQ. And so we could do this, but we have to make a further relaxation. The relaxation here is that we can only achieve a subclass of degree D polynomials, namely those where it has this very specific structure that is just you apply the degree D polynomials on each small chunk of the inputs, and then you concatenate them together. Okay. And the reason why this works is that if you chunk up the inputs into many, many small chunks, then your functions sort of does not blow up as much. And so when you apply your quadratic evaluation here, you can still achieve compression for the hash function. So yeah, here you do some tensor steps so that eventually it's still sort of it's still correlation-intractable against degree D polynomials, but you only need a quadratic thing applied to these steps. Okay. So that's basically the idea. Right. So now I've shown you how the template works and two candidate constructions of CI hashing, either from MQ or from higher degree analogs. So let's go back to trying to achieve NIZK. And the road looks something like this, right? for the first and the second line, we can directly get NIZK. But what about from the third line? I said we have some relaxation. Is that relaxation enough? It turns out that it is enough. And the reason is that with parallel repetitions, you can coerce the bad functions, the bad challenge functions, to be of this form, to be a concatenated polynomial, or approximated by one. Okay, so parallel repetition of a protocol means that you just execute that protocol many, many times in parallel. So in the first round, you send all of the encryptions from all of the executions, and then you receive all the challenge, and you send all the responses at once. And then also you would, to apply the Fiat-Shamir transformations, you just add this one, and then you get all the challenges. And then you notice now that this bad challenge function actually has the concatenated format. It is the concatenation of the bad challenge function applied to each of the first messages. And so we get the statement that we want. Okay.
Doesn't this parallel repetition have issues with the zero knowledge?
No.
That's a challenge, right? For example, pre-coloring parallel repetition.
Yeah. So for Fiat-Shamir to work, we only need honest verifier zero knowledge for the base protocol, which is preserved when you do parallel repetitions. Yeah.
Is it true in the standard model?
What do you mean standard?
Like in the random model, yes.
Yeah. No, it even works for this. So the result that you were saying is somehow the zero knowledge of the interactive protocol against malicious verifier. It is intimately connected to whether you can use Fiat-Shamir to obtain this. And so if you can apply Fiat-Shamir to this, then it means that the sort of original protocol is not zero, not zero knowledge, or parallel repetition, whatever. Yeah, that was a technical point. You don't need to follow it. Okay. So that's that. And as promised, I might get to the Dense-Sparse LPN stuff. But now let me just say, here's the template so far. We have achieved NIZK. If we want the extra statistical zero knowledge property, what we want is that in the first message, you want an encryption scheme where somehow you can switch the public key, and it actually makes your encryptions statistically indistinguishable from random. And that would lead you to have a statistical zero knowledge property, because now the messages are just sort of the underlying plain text are just erased from the interaction, essentially. And so you need this lossy version of public key encryptions, and you still need approximately linear decryptions. And so we achieve this from this new assumption that we have called Dense-Sparse LPN. And it's actually not possible. We showed that if we try to build it from just LPN, then it would have this horrible correctness error. And so it is so horrible that we cannot plug it in the templates. But with Dense-Sparse LPN, the key point here is that with this new variant, we can somehow achieve a better control over the error buildup. And so the final error is only 1 over poly of lambda. And that is enough to plug into the template. Okay. So maybe
the first line is lossy PTA from LPN. So is this a load mount, or is this just for the construction considered?
This one.
Is it a load mount?
It's not. Anyway, yeah. It's that you try a template and it gives you this.
But potentially you could do it.
Yeah, potentially. Yeah, that would be a great advance. Yeah. Okay. So I had a few slides here about LPN stuff. So maybe let me just flash you very quickly what is LPN and why does the construction fit. Okay. So LPN is this sort of noisy learning problem where the noise is a sparse noise. this epsilon here, you just have random locations being 1, and then the rest of the locations being 0. And then it should be the case that this SA plus E should look random, computationally indistinguishable from random, even given this big matrix A. You could imagine that without this error, you can just use Gaussian elimination to find this. But with this error, it just gets exponentially harder to do so. Okay, and in fact, this is essentially the best attack that we know right now, which is just that you hope to find some errorless locations, and then you use Gaussian elimination to solve for the secrets. And we don't know any better attack here. And so the time complexity is basically this 2 to the some constant times epsilon times n. And yeah, this is LPN. So how might we construct this lossy PKE schemes from LPN? The idea here is that your public key should be this LPN sample, this A and then B, which should be SA plus E. Here I write it in matrix form, but you can just think of it as having many LPN samples, so like S1A plus E1, S2A plus E2, and so on. So you have a matrix. You collect them into a matrix B. Good. And then the lossy key is when you don't do this. B is just a random matrix. Okay. To encrypt this message mu with this public key PK, you would sample a random sparse vector X, and then you will multiply X with the public key, and then you add in the message at the end. And you want to sort of repetition code it so that you can later on decrypt from lots of errors. Okay. And in the lossy mode here, what you want is that the ciphertext should be statistically erased. So, which means that this B times X should be statistically random, even given A times X. For the decryption process, with the secret key S, you can now try to eliminate this A times X term, and then you just get the mu repetition coded, and then you have some noise. And if the noise is not that much, you can take the majority, and then you will get your results with high probability. Okay, and how high is it? Well, we require that the error in this majority decoding is subconstant, or ideally like 1 over poly of the security parameter. Okay. And essentially, in this lossy mode, if you want to have some kind of compression, then you would need some kind of statistical indistinguishability. Then you must need that A times X somehow loses information about X. And then by this leftover hash lemma, you can show the statistical indistinguishability. Okay, so here are the 2 properties that we need that I claim are somehow contradictory when you just rely on LPN. Okay, so let's see, we are at time. So maybe let me not show this, but I claim that if you work this out, then you'll find that you cannot achieve these 2 properties at the same time, and this is why we need our new assumption. So let me skip through the next slide. Okay, and let me go to summary. So the summary here is that we built this new construction of NIZK from 2 well-studied post-quantum assumptions, LPN and MQ. And by doing so, we expand the sort of diversity of NIZK constructions, especially in the post-quantum setting. And also, I think our work leaves a lot of future directions open. Namely, can we try to achieve NIZK from purely some kind of code-based or some kind of multivariate-based assumptions? So LPN and MQ, we're relying on them together, but can we remove one of the 2? Also, can we try to now that we have gotten NIZK, then we try to get these more advanced proof systems. And also, finally, it would be great if people study these higher analogs of MQ more thoroughly and try to come up with just sort of better study of what are the parameters for which it is secure. So with that, I'd like to thank you. And yeah, if you have any questions.